Hello everyone. Welcome to another episode of Deep Dive Knowledge Talk. Welcome. Today we delve into chain of thought, how step-by-step reasoning empowers LLMs for complex arithmetic and symbolic tasks. We'll explore its significance in enhancing AI performance and shaping future designs for truly intelligent systems. Can you explain the significance of using chain of thought CoT in enhancing the capabilities of large language models, particularly in the context of arithmetic and symbolic reasoning tasks?
Using chain of thought CoT is like giving a child a step-by-step recipe to bake a cake instead of just telling them to make a cake. So when a child follows the recipe, they understand what to do at each stage, which helps them successfully create the cake. Similarly, when large language models LLMs are instructed to generate a sequence of intermediate steps or a chain of thought, so they can tackle arithmetic and symbolic reasoning tasks more effectively. The significance of CoT lies in its ability to help these models perform more complex, like serial computations. Think of it like solving a puzzle, rather than trying to fit all the pieces together at once. So, breaking it down into smaller parts makes it easier to see how each piece connects. So by generating these intermediate steps, the model gains extra information and efficient strategies for solving problems, much like a child learns better by following each step in the recipe. Moreover, even when the model is prompted to think step by step without specific guidance, it still manages to improve its reasoning-like capabilities. This really shows that the act of thinking through a problem, even if some of the reasoning steps are incorrect, can lead to better outcomes. Just as a child might learn from mistakes while baking In summary, CoT enhances LLMs by allowing them to process and solve problems in a more organized and thoughtful manner, leading to improved accuracy in tasks that require arithmetic and symbolic reasoning. So,
how does the theoretical framework presented in the study help in understanding the limitations of constant depth transformers before introducing chain of thought CoT, particularly regarding their capabilities in solving problems within specific complexity classes like true zero and add zero?
The theoretical framework helps us understand the limitations of constant depth transformers by comparing their capabilities to solve problems in specific complexity classes. So, like add zero and tie zero, imagine constant depth transformers as a group of workers who can only work on very simple tasks at the same time, sort of like sorting blocks by color. They can handle so many tasks quickly, but they struggle with more complex challenges that require a series of steps, like building a tall tower with those blocks. Without chain of thought CoT, these transformers are limited to solving problems in the add zero class, which represents very simple tasks that can be done in parallel. However, when faced with more complex tasks in the type 0 class, which require a bit more thought and are harder to solve using parallel methods, constant depths, like transformers, fall short. The framework shows that by incorporating CoT, these transformers can perform a whole series of steps, so similar to a worker who takes time to think through how to build that tower step by step, with steps of CoT, so they can solve any problem that can be handled by Boolean circuits of size. So this means they can tackle more complex tasks that require sequential reasoning, which is essential for solving problems that are inherently serial in nature. The experiments also reveal that enabling CoT significantly boosts the transformer's ability to solve difficult problems, such as permutation composition or iterated squaring, which are not so easily solved by parallel computation alone. However, it's important to note that even with CoT, there are limits, like logarithmically, so many CoT steps won't allow the transformer to compute functions beyond the add zero class. In summary, the theoretical framework really highlights how constant depth transformers can struggle with complex problems without CoT, but by using CoT they gain the ability to think through tasks more effectively, enhancing their problem-solving capabilities significantly so.
What empirical evidence was gathered in the study to support the kind of claim that enabling chain of thought CoT significantly improves the performance of transformers on tasks that are really challenging for parallel computation?
The empirical evidence gathered in the study demonstrates that enabling chain of thought CoT significantly enhances the performance of transformers on tasks that are challenging for parallel computation. So, to illustrate this, researchers conducted experiments with transformers on 4 core problems: modular addition, permutation composition, iterated squaring, and the circuit value problem. So in these experiments, the transformers were trained using a large amount of synthetic data, with some models utilizing CoT while others did not like. So this setup allowed the researchers to directly compare the performance of the models So the findings showed that when CoT was enabled, the accuracy of the transformers improved dramatically, particularly on tasks that require a series of steps and are inherently serial in nature, such as permutation, composition, and iterated like squaring. For example, while modular addition can be solved easily in parallel, the more complex tasks like permutation, composition are difficult to handle without a thoughtful, step-by-step kind of approach. The results indicate that the CoT empowers the transformers to navigate these challenging problems more effectively, highlighting the importance of generating intermediate steps in improving their reasoning capabilities. So, in summary, the empirical evidence from the experiments clearly supports the claim that enabling CoT enhances the ability of transformers to tackle tasks that are really tough for parallel computation, making them more expressive and capable of solving complex problems.
What are the implications of the findings regarding chain of thought CoT for the future design of transformer architectures, particularly concerning their depth and computational strategies?
The findings regarding chain of thought should have really important implications for the future design of transformer architectures, especially in terms of their depth and computational strategies. Firstly, the research indicates that transformers equipped with CoT can effectively handle complex problems that require a whole series of sequential steps, which highlights the need for deeper architectures. Without CoT, the ability of a transformer to perform serial computations is limited by its depth, which is often fixed. So, by enabling CoT, transformers can generate intermediate tokens that guide them through the reasoning process, allowing for a greater number of serial computations. This suggests that future designs might benefit from increasing the depth of transformers to further enhance their capacity for complex reasoning tasks. So, additionally, the findings imply that incorporating CoT can provide a statistical advantage. So, since CoT generates more labels and additional information about the ground truth, it can improve the model's learning whole process. So this could motivate designers to create loss functions that leverage the chain of thought as labels, enabling the model to learn more effectively from the reasoning steps it generates. Moreover, while the research shows that logarithmically, so many CoT steps do not extend the capabilities of transformers beyond certain complexity classes, the ability to perform well with a limited number of intermediate steps still emphasizes the importance of developing strategies that facilitate the whole generation of these thought processes. In summary, the implications of the findings suggest that future transformer architectures could be designed with greater depth and integrated CoT mechanisms, allowing for enhanced reasoning capabilities and improved performance on complex tasks that actually require serial computations.
What potential directions for future research does the study suggest in order to further explore and enhance the effectiveness of chain of thought CoT in transformer models, particularly in relation to their limitations and the complexity of problems they can solve?
The study suggests several potential directions for future research to further explore and enhance the effectiveness of chain of thought CoT in transformer models, particularly regarding their limitations and the complexity of problems they can solve. One direction is to actually investigate the statistical advantages of CoT in more detail. So since CoT provides additional labels and more information about the ground truth, researchers could explore how to design loss functions that effectively incorporate the chain of thought as labels. This could really improve the model's learning process and performance on complex tasks. Another area of research could focus on understanding the limitations of CoT in terms of the types of problems transformers can solve, While the study indicates that CoT allows for solving complex problems that require serial computations, it also notes that there are bounds to what actually can be achieved with a limited number of CoT steps. So, future studies could aim to identify these boundaries more precisely and explore ways to extend the capabilities of transformers beyond current complexity classes. Additionally, researchers might consider experimenting with different configurations of CoT, such as varying the number of intermediate steps or the structure of the generated kind of sequences. So this could provide insights into how different CoT strategies impact the performance of transformers on various tasks. Lastly, empirical evaluations could be expanded to include a wider range of problems just beyond the 4 core tasks studied. By testing transformers equipped with CoTs on diverse challenges, so researchers could gain a better understanding of the generalizability of CoTs and its effectiveness across different domains. In summary, so future research could focus on refining loss functions, exploring the limitations of CoT, experimenting with different configurations, and expanding empirical evaluations to enhance the understanding and effectiveness of CoTs and some CoTs like.
How do the findings related to chain of thought CoT in the study contribute to the broader understanding of computational complexity in neural networks, and what lessons can be drawn regarding the design of future AI systems? Sort of like.
The findings related to chain of thought CoT contribute significantly to the broader understanding of computational complexity in neural networks by highlighting how structured reasoning can actually enhance the problem-solving capabilities of models. By demonstrating that generating intermediate steps allows transformers to perform inherently serial computation, so the study sheds light on the limitations of traditional architectures that rely solely on parallel processing. So one key lesson drawn from these findings is the importance of incorporating mechanisms that allow for sequential reasoning in the design of future AI systems. Just as a well-structured recipe guides a cook through the cooking process, CoT provides a framework for models to navigate complex tasks step by step. So this suggests that future AI systems could benefit from designs that explicitly include pathways for reasoning through problems rather than just providing direct answers. Moreover, the study indicates that even incorrect reasoning steps can still improve performance, which suggests that the process of reasoning itself is so valuable. This insight encourages a shift in focus from merely achieving correct outputs to fostering models that can actually explore and learn from various reasoning paths. Additionally, the findings really emphasize the need for a deeper understanding of the expressiveness of neural network. By analyzing how CoT enhances the capabilities of transformers, researchers can better comprehend the types of problems that different architectures can solve, so leading to more effective and efficient designs. So, in summary, the insights gained from the study of CoT inform the development of future AI systems by advocating for the integration of structured reasoning processes, recognizing the value of exploratory reasoning, and enhancing our understanding of neural network expressiveness in relation to computational complexity.
So thank you for joining us on this fascinating journey into the world of artificial intelligence. Tonight we delve deep into the transformative power of chain of thought, or CoT, in enhancing large language models. We've seen how CoT acts as a crucial recipe for these models, breaking down complex arithmetic and symbolic reasoning problems into sort of manageable step-by-step processes. This structured approach allows models to tackle computations that would otherwise be beyond their reach. So our discussion highlighted the fundamental theoretical insight that CoT enables sequential reasoning, overcoming the inherent limitations of standard transformer architectures when faced with intricate multi-step challenges. The empirical evidence we explored truly underscored this, so demonstrating significant performance improvements in tasks like permutation composition and iterated squaring where parallel processing alone falls short. Just looking ahead, the insights from this episode strongly suggest that the next generation of AI systems will benefit immensely from deeper architectures and integrated CoT mechanisms, fostering more robust reasoning capabilities. There's so exciting work to be done in refining how we train these models, exploring the boundaries of CoT, and expanding its application across an even wider array of tasks. It's clear that fostering structured sequential problem-solving is paramount for the future of intelligent systems, embracing even those exploratory paths to a solution. So thank you again for tuning in. So we look forward to seeing you next time for another insightful conversation.